Let's continue now. We are in the middle of proving the structure theorem for finite fields, which is this statement. It says a lot of information, it gives a lot of information about finite fields. We've proved a couple of these statements, and let's now do the remaining parts. So far we've proved D, and we have actually not proved C, but I told you that I'll skip the proof because it uses some group theory facts which I don't want to do now. And now let's now prove A, which is the main theorem that we want to focus on. So A which is exactly the existence of a finite field. Existence, so I'll write it right here, existence of fields of order Q. Remember, in the example that I did in the before the stating the theorem in the last video, we constructed a field of order 4 by looking at F2 and a degree 2 irreducible polynomial and going modulo that. But I also commented in the last video that in general this method is difficult to implement, because how do you know that there is a irreducible polynomial of degree r over Fp? If it exists, then we can go modulo it and get the field that we want, which is p power r. So we are going to take a different approach using what we have already observed, which is that elements of such a field, if it exists, are going to be roots of x power q minus q, x. So what we are going to do is use a theorem that I have proved earlier in the video, earlier in the course, about splitting fields. So let us do the following. So let us consider the polynomial x power q minus x in Fpx. We already know that every field, every polynomial over a field has a splitting field. If you go back and look at that splitting fields video, you will see that we proved that in general capital F was any field, small f was any polynomial, and we constructed a splitting field. So that was not specific to finite fields or infinite fields or anything like that. So we will apply that to Fp and x power q minus x. So let us take some splitting field. So let L be a splitting field. Actually, we do want to take splitting field, but I will state it like this so that it becomes slightly easier to understand what I am saying. Let L be any field extension of Fp over which x power q minus x splits completely. So we have such a field. So you have Fp here and some extension exists where x power q minus x splits completely. That means it is a product of linear polynomials. What we want is that just look at the roots of this. By part D that I have already proved, remember part D that I have already proved that any field of order q that we are now trying to show exists is going to be exactly the roots of x power q minus x. What I have now done is I have constructed a big field where x power q minus x splits completely. That means L contains all the roots of x power q minus x. We know that K is supposed to be the desired field K of order q is supposed to be this collection of roots of this. So we are going to just take K to be alpha in L such that alpha is a root of x power q minus x. We know that, I am just rewriting that, we know that K, if it exists, is supposed to be like this. So I will define K like this and hope for the best. What do we need to show? It is a subset of L now. We get what we want if we show that K is a field, right? If K is a field, it certainly has, we also need to show that containing q elements. So let's say we are done if K is a field of order Q. So I need to also show that it has order Q. So I need to show that it is a field and that it is order Q. So two things, K has Q elements. So there are two things, I will break up the proof into two parts. K has Q elements and that K is a field. So this I will not do in detail because I didn't do the notion of multiple roots of a polynomial in detail. So I am going to just quickly tell you that K has Q elements, because how can it have fewer than Q elements? If it has fewer than Q elements, that means some root is a multiple root. If K has less than Q elements, so remember K is the collection of roots of x power Q minus x. It's an exercise that there are at most Q of such elements. So but it can be in general less than Q. So certainly what I am saying is that maybe I will do this as an exercise later. Order of K is less than or equal to Q. We know this. If you have a polynomial or a field of order Q, degree Q, its roots is at most Q. And we are now trying to show that it is exactly Q. Suppose it has less than Q elements, then one root must be a multiple root. What I mean is, you can write x power Q minus x factor in Lx. You can factor in Lx x power Q minus x as x minus alpha 1, x minus alpha 2, all the way up to x minus alpha Q. Because this is degree Q and you have every factor is a linear factor, so there must be Q linear factors. Right? There must be Q linear factors. If the Q linear factors are all distinct, then you have Q distinct roots, and that is the claim that I am making. Suppose Q has fewer than K has fewer than K elements, Q elements, that means something is repeated. So if order of K is strictly less than Q, then we have alpha I is equal to alpha j for some I not equal to j. So without loss of generality, so we suppose alpha 1 is equal to alpha 2. So some factor is repeated, so it's called a multiple root. So alpha 1 is called a multiple root. But then I am going to rewrite this x minus x power Q minus x as x minus alpha 1 whole squared times gx. The remaining thing I don't care, right? Because alpha 1 is equal to alpha 2. The first two things I'll combine and write it like this. Now if you differentiate both sides, what do we get? We get Q times x power Q minus 1 minus 1, that's the derivative of the left hand side. The right hand side I am going to use the product rule. So I will have x minus alpha 1 whole squared times g prime x plus gx times 2 times gx times x minus alpha 1, right? So I have this. Now plug in x equal to alpha 1. What do I get? I get, so this is actually equal to minus 1. Why is that? Because Q is 0, right? Q is p power r. That means Q is 0 in L. If L contains z mod pz, that means p is 0. Once p is 0, p squared is 0, p cubed is 0, p power r is 0. So Q is 0, that means minus 1. So if you plug in minus alpha equal to x on the left hand side, nothing changes because it's a constant. On the right hand side, you get alpha 1 minus alpha 1 whole squared times g prime alpha 1 plus 2 times g of alpha 1 times alpha 1 minus alpha 1. But this is 0 because this is 0 and this is 0. But that means minus 1 equal to 0. That means 1 equal to 0 because I can take negative of both sides. This is not possible. because in any field you have at least two elements and 0 and 1 are going to be different. So this is not possible. So that means no root can repeat, that is the point. A multiple root must be a common root of the polynomial and its derivative. But the derivative of the special polynomial that we are interested in here, x power q minus x, is actually minus 1. So it cannot have any roots. So the derivative and the polynomial can't have common roots. So the polynomial in question has q distinct roots. So k has q elements. So now second part is k is a field. This is a very rare situation. We are taking a polynomial and taking its roots. Very rarely do they form a field. Roots of a polynomial rarely form a field. But it happens over finite fields and these specific polynomials. So what do we have to show? So I am going to skip most easy things. What are we going to show? So we want to show 0 is there, 1 is there, minus 1 is there. If alpha and beta are in k, and let's say alpha is not 0, then alpha inverse is there, alpha plus beta is there, alpha beta is there, and so on. So these are the conditions, right? We have a subset of k, of L, and we are claiming that it's a field. That means take two elements, their product is there, their inverse sum is there. If non-zero, then its inverse is there, 0 is there, 1 is there, and so on. Okay, so let's check all these things one by one. 0 power q is certainly 0, that means 0 is in k. Remember the definition of k. K is the set of roots of x power q minus x. So if any root, any element of L satisfies x power q minus x, it is in k. So I hope you are following everything. If not, please pause the video, think about it. This is the most crucial part of the whole structure theorem. In fact, A and B are the most important statements. So 0 is there, 1 power q is 1, so 1 is there, right? Similarly, minus 1 power q is either minus 1, so there are two possibilities, right? If it is 1 if q is even, minus 1 if q is odd. In this case, of course, we are done because minus 1 power q is minus 1 and hence minus 1 is in k. But if q is even, also we are done because if q is even, that means q is of the form 2 power r, right? The only even numbers which are powers of primes are powers of 2, in which case minus 1 is 1 because it's characteristic to 2. So 2 equal to 0 means 1 plus 1 equal to 0, that means 1 equal to minus 1. So again in this case minus 1 power q is actually equal to 1, which is equal to minus 1. So minus 1 is in k. Okay, and if alpha power q is alpha and alpha is non-zero, then alpha inverse exists in L and its power q is also alpha power q minus 1, which is alpha power minus 1. Similarly, the easier thing is alpha beta are in k, then alpha beta is in k. Okay, so this is easy. So the main thing to check is the sum. So all these things are easy. Main thing to check is the sum. Let's say alpha and beta are in k. We want to show that alpha plus beta is in k. And this is where the characteristic again comes to our rescue. Again, let me remind you, what is the meaning of being in k? That means its power, its qth power is itself. So let's take the qth power, alpha plus beta power q. If you apply binomial theorem, you get alpha power q, q choose 1, alpha power q minus 1 beta, q choose 2, alpha power q minus 2 beta squared, dot dot dot, q choose q minus 1, alpha beta power q minus 1 plus beta power q, right? This is the binomial expansion of alpha plus beta power q. Now this is a simple fact which I think came up in the earlier part of the course. Since q is of the form p power r, you can show that q choose I is 0 for all I between Okay, so all you need to do is simply write q power I as q factorial divided by factorial times q minus I factorial, and first prove it for p itself, in which case it is trivial, then by induction extend it to powers of q. So I am going to skip this. Again, this is going to lead me in a different direction, so I will skip this. Sorry, actually I should not say this, it is not 0. In general, I can say it is divisible by, p for all I between 1 and q minus 1, because there will be a factor of p in the numerator that will survive after cancelling all the factors in the denominator. So it is divisible by p, but if it is divisible by p, we are in a field which contains Fp whose characteristic is p, that means p is 0 in Fp, hence p is 0 in L. So that means this is 0, this is 0, this is 0. So every intermediate term is 0. So this is alpha power q plus beta power q. Only the first and the last term survive, but alpha and beta are in k. So alpha power q is alpha, beta power q is beta. So alpha plus beta whole power q is alpha plus beta. So this is an indirect proof, but it's a very nice proof. So k is a field of order q. So we have shown that for every prime power there is a field of that order. So let me now prove part B, which is the second most important part of this whole structure theorem. Let k and k prime be two fields of order q. We want to show that k and k prime are isomorphic as fields, of course, which is same as rings. Okay, so let's prove that. What we have is by part, so I forget the part. So part B is the statement that any two fields of order q are isomorphic. We know part C, though we didn't prove it, we are going to make use of it. Part C says that k cross, which is the multiplicative group of non-zero elements of k, is generated by a single element. Let's call that alpha. Right? So in particular, we must have that k is Fp alpha. Right? Remember, all these extensions are finite. K and k prime are finite fields, so they are finite extensions of Fp. Because certainly, if a finite field is there, the dimension is also finite. So it's a finite extension, so it's an algebraic extension, and in fact, alpha generates it, because remember, this is easy. Because what is k? It is actually 0, 1, alpha, alpha squared up to alpha power q minus 1. Because other than 0, the remaining elements are in k cross, which is a cyclic group of order q minus 1 generated by alpha. So k cross contains elements of the form 1 alpha, alpha squared, alpha power q minus 1, and k of course contains 0, so k is this. What is the meaning of being Fp alpha? That means every element of k is supposed to be a polynomial in alpha. In fact, every element of k is a very simple polynomial in alpha. Every element of k is either 0 or in fact a power of alpha. So this is certainly true. In fact, much more than this is true. This is a very weak statement. I am saying that this is certainly true. What we have here is a much stronger statement than this, but I will only use this fact. So, okay, now we can actually draw this picture. K Fp and k is Fp alpha. What is the degree of this extension? It is r, right? Because this has q power r elements, sorry, this has q elements, which is p power r, and this has p elements, and we used counting argument in the earlier video, which says that if the elements are p power r here over a field of order p, the dimension is r. So the irreducible polynomial, so let f be in Fpx be the irreducible polynomial of alpha over Fp. It is an algebraic element, so we can take its irreducible polynomial. Since k colon Fp is equal to R, the degree of F is R. Right? This is way back when we talked about degree of field extensions versus degree of elements. So degree of F itself is R. Also, we know that F divides x power q minus x. Why is that? The reason is alpha power q is equal to alpha. Alpha being an element of k, and by part maybe d or d, I think, we showed that every element of k is a root of x power q minus x. So in particular, alpha is a root of x power q minus x. But F is the irreducible polynomial of alpha. That means F divides that. Now, k prime, which is a field of order q, also consists of roots of x power q minus x. Right? Also consists of roots of x power q minus x. So, since F divides x power q minus x, F must have a root alpha prime in k prime. Okay, so this is a bit tricky, but what I am saying is that k is there, it is an extension of Fp of degree R. Similarly, k prime is there, this is also an extension of degree R, because k prime also contains p power R elements. Alpha is here, right? The irreducible polynomial of alpha is small f, which lives over capital Fp. That small f divides x power q minus x. X power q minus x splits completely in k prime, because k prime exactly consists of roots of x power q minus x. That means F must have a root in k prime. I am calling that alpha. What you have to be careful about is you can't compare k and k prime. They can be very different. They are not contained in each other, or they are not contained in a bigger field. So you can't say alpha is in k prime. That will be incorrect. But we can say that F has a root alpha prime in k prime. Then what would be, so I am going to squeeze in here Fp alpha prime, and I have k here, prime here. So Fp alpha prime is here, which is the root of, so now I will remove that R here. Fp alpha prime is the field generated by alpha prime, where alpha prime is the root of F. So F must be the irreducible polynomial of alpha prime over Fp, because F is an irreducible polynomial, alpha prime is a root of F, so F must be the irreducible polynomial of alpha prime. But then degree of F is R. So this must be R, right? Degree of an extension is equal to degree of an extension generated by a single element is equal to the degree of that element. But this whole thing is also R, right? That is because k prime has q elements, which is p power R, so this is R. That means this must be 1. When is something 1? When is a degree of field extension 1? So k prime is equal to Fp alpha prime. But what is Fp alpha prime? This is another way of writing Fpx modulo F, right? This was done in the beginning of our field theory part, because anytime you join an algebraic element, it is isomorphic to this ring modulo the ideal generated by the irreducible polynomial of that algebraic element. But this is also same as Fp alpha, because Fp alpha is also obtained by going modulo the irreducible polynomial of alpha, which is F, but of course that's k. Okay, so k is isomorphic to k prime as required. So this completes the proof of part B. So part B, and remember part B and A are the important things for us. Part B was that any two fields of order q are isomorphic. So this I have shown. I have shown that there is a field of order q, we have shown today in the beginning. In the last video I have shown that so not showed, but I have commented that this is true because of a fact in group theory, and I will not prove that. So C is taken care of, and in the last video we have proved D, that every field of order q consists of roots of x power q minus x. So that leaves two parts. So I am going to go fast over these, and I would rather give examples to illustrate this instead of proving this, because the proof can get a bit tricky. So I will, instead of proving all directions, both directions, I will prove some parts of it. So let's now come to E. So let's come to E. E was talking about subfields of FQ. So one direction is clear, okay, that is because, so let's say Q is p power r and Q prime is p power k. Okay, suppose, so okay, also a notation. I should have written this before writing that. A field of order q will be denoted by FQ. By the part B, any two fields of order q are isomorphic. So up to isomorphism, I am allowed to use this symbol to denote any two fields. Okay, so any field of order q will be denoted by FQ. So now I am interested in subfields of FQ. So suppose FQ prime is contained in FQ. That means if you draw the picture, we have FP, FQ prime, FQ, right? And what is the degrees of these extensions? What is the degree of FQ prime over FP? Because Q prime is p power k, I claim this is k, right? Because Q prime is p power k, the dimension will have to be the exponent. What is the degree of this? That's r. That is what we have been doing. Q is p power r, so this is r. So by the multiplicativity of field extension, degrees of field extensions, we know that k divides r. In fact, this will be r by k. So then the product of these two is r. So the statement we have just proved is that if FQ, let me write it like this, even though it's a bit messy, but if Fp power r contains FQ, Fp power k, that means k divides r. The converse is also part of the statement. The converse I will not prove in detail, but only comment on the following. For the converse, suppose k divides r, okay, suppose k divides r, the fact here is a simple numerical verification, which I will leave this as an exercise for you. If k divides r, you can just, this you can find in any book, and one can show that p power k minus 1 divides p power r minus 1. So I will skip this. If k divides r, so this is if k divides r. Okay, so if k divides r, what I am saying is, for example, 2 divides 4, that means p squared minus 1 divides p power 4 minus 1. This is because p power 4 minus 1 can be written as p squared minus 1 times p squared plus 1. Okay, something as simple as that, but in general you need to prove this. So if I will assume this, if k divides r, then p power k minus 1 divides p power r minus 1. In this case, let's look at FQ. Remember, we are trying to show that FQ contains FP. Q is, again, let me remind you, p power r, Q prime is p power k. I am assuming k divides r, and I am trying to show that FQ contains FQ prime. FQ cross is a group of order, cyclic group even, of order p power r minus 1. Okay, q minus 1. So I am trying to avoid q here because there is q and q prime, it's a bit confusing. So this is p power r. Fq cross is, it's a cyclic group of order p power r minus 1. Since p power k minus 1 divides p power r minus 1, there exists an element of, let's call it beta, of order p power k minus 1 in f p power r cross. So this is a group theory statement. If you have a group, cyclic group of order 100, any number dividing 100, there is an element of that order, right? So this is a statement about cyclic groups. P power k minus 1 divides p power r minus 1. So there exists an element beta of order p power k minus 1. So now the group generated by beta are the roots, is exactly the set of roots of x power p power k minus 1 equal to 1, right? Roots of the polynomial this, because if b has order p power k minus 1 means b power p power k minus 1 is equal to 1. Similarly, b square has that property, b cubed has that property, all powers of b have that property. Now if you define L to be 0, beta, beta squared and so on, then by the same argument that we have used earlier, L is a field of order p power k exactly equal to p power k, because there will be p power k minus 1 elements here and you are adding 0 to it. So this is a field of order p power k, and hence, so and L is of course in k, L is of course in fq, because these are all elements in fq, right? So beta is in fp power r, so that means these are all in fp power r, hence L is isomorphic to fp power k, right? Because it's a field of order p power k, so it is isomorphic to the unique field of that order. So fp power r contains fp power k. Okay, so this is part D. So finally, let me quickly prove part E, which finishes this statement about, this is part E, I think. So I'm going to do part F, the final part. So this is the irreducible factors of x power q minus x in fpx. The last part is this. Okay, so let's prove this. So and we remember, so let me show you the theorem. So the irreducible factors of x power q minus x are the irreducible polynomials in fpx whose degree divides r. Okay, so let's prove this. So let g in fpx be irreducible of degree k. Okay, so suppose it is irreducible of degree k. So now we are going to work with k, which is fp power r sitting over fp. This is a field extension of degree r, and remember x power q minus x splits completely in fp power r. It is in fact x minus each element of fpr and you take the product. So this is degree r extension. So now suppose g divides x power q minus x in fpx. So it is same as dividing in fqx, but I will not stress that here. Suppose g divides this in fpx, then g splits completely in k, which is fp power r, right? Because x power q minus x splits completely. So g being a divisor of it also splits completely. This implies g has a root beta in FPR, right? So g has a root in FPR, so let's call that beta. So what I will now do is I will expand this. What I get is FP beta FP, right? So that means, and what is the degree of this? Degree of G is equal to the extension field degree, right? And we call that K. So K is the degree of K, of G. So the degree of the field extension is K. This is again degree of a field extension generated by an algebraic element is equal to the degree of that particular algebraic element. But that means this whole thing is R, right? So K divides R. So if G divides that, K divides R. On the other hand, suppose K divides R. Let beta in L, so okay, let L be an extension of FP in which G has a root. So what I am saying is that you have a root, let's call it beta again. Remember that for any field and any polynomial over there, you can construct a bigger field in which it has a root, because G is irreducible. All you need to do is go modulo G, Fpx mod G will do the job. So now I can actually take Fp beta L. So now what is the degree of Fp beta? By the same reason as before, Fp beta over Fp is equal to degree of G, which is K. So that means this is K. Now by the previous part, since we are assuming K divides R, by part E, Fp power R contains a field which is isomorphic to Fp power K by part E, right? This is exactly part E. We have shown in part E, if K divides R, Fp power R contains Fp power K. So F contains Fp power R contains Fp power K, which is actually isomorphic to Fp beta, because Fp beta has a degree K over this. That means this is Fp power K, right? Because this is P elements, this dimension is K, that means this is P power K elements. So that means the corresponding element, there is an isomorphism here, this is contained in this. In sort of, you can put this, loosely speaking, you can put this line here. That means you can think of this as a subfield of this. So because of that, because Fp beta can be thought of as a subfield of Fp R, G has a root in Fp power R. All we need to do is look at the isomorphism of a subfield and look at the image of beta. That means it has a root in Fpr. But that means, let's say that root is called B prime in Fpr. But B prime is a root of x power q minus x also, because every element of Fp power R is a root of x power q minus x, where q is p power R. So G is the irreducible polynomial of beta prime. X power q minus x is another polynomial that has beta prime as a root. Hence, G divides x power q minus x. Actually in Fpx I will say, and this last part I will wave my hands. Division, if you have a field extension and two polynomials in the smaller field, and if one divides the other in the bigger field, it divides in the smaller field also. because the division process doesn't keep track of which field you are working with, assuming you have started with the polynomials in the same base field. Okay, so that's an aside, but we conclude that G divides x power q minus x. So if k divides R, if you have G irreducible polynomial of degree k, it divides x power q minus x. So now let's go back to the statement of the theorem. We showed that the irreducible factors of x power q minus x are exactly the irreducible polynomials whose degree divides R, because we have shown that any irreducible factor of x power q minus x has a degree dividing R, and we have also shown that if you have an irreducible polynomial whose degree divides R, it divides x power q minus 1, x power q minus x. So this is done, and before that we have shown E. So all the parts are done. So this is the proof of the structure theorem, and I admit that I have gone very fast maybe in the last two parts, but the statements are important, and I will do some examples in the next video to illustrate how to apply those results. But the most important thing to keep in mind is that there exists a field of order q always. Any two fields of order q are isomorphic, and of course q is p power r. That's very important, because if q is not p power r, it cannot exist. That we have already shown. Only possible finite fields have order p power r. And we have also mentioned that the multiplicative group of any finite field is a cyclic group of order q minus 1, and elements of a field of order q are roots of x power q minus x. And then we have two statements about subfields of fq and irreducible factors of x power q minus x. So let me stop this video here. This completes the proof of the structure theorem and also completes the course, except that I will do now a video with examples on finite fields, and then I will do one or two videos on problems. Thank you.